Hello, and welcome to this video lecture on section 1.2 from the book, talking about solutions to differential equations. So what we're going to talk about in this video lecture is sort of what solutions to differential equations look like and how to go about solving them, and talk about these initial value problems that you've probably seen in the book, and more explain sort of what they are and how they work. So let's go ahead and jump into that. So in the book, they talk about this differential equation. This differential equation here that came from the population growth of the rats in the field or whatever. And they get a solution to it that looks like this. P of t, the solution, is 900 plus c e to the t over 2. Now don't worry in particular about how they got that solution. We'll talk about that in the next couple sections. But it just looks like this, where this c is some random constant that they haven't specified at all. And the point is it's actually supposed to be there. So if you think of normal integral problems you did in calculus, right, you integrate and you get this integration constant c that really is not determined until you know other information. Well, that's the same idea here. You're solving a differential equation using a type of integral type thing. So you're going to have an integration constant that you need more information to determine. So first let's take this equation right here. In this sort of setup we have this 900 plus c e to the t over 2. And take a look at what that looks like graphically. So I'm going to pull up Maple. We can look at some stuff in Maple. So here I have set up a sort of situation where we have to solve this equation. So I've used x of t here instead of p of t, but everything else here is still the same. 0.5x minus 450. I've solved it for some x0 equals d, and then I've graphed some things down here. So the green arrows are referred to as a direction field for the problem. And that is just at every point I draw an arrow that is the right-hand side of the equation. So at the point 0.5, 900, I draw 0.5 times 900, which is 450, minus 450 is 0, so I draw a horizontal tangent line at 900. As you can see, that's actually uniform across the entire x direction, the t direction, sorry. The lines are always horizontal here, they're always the same slope at every point, and that happens because this side here does not depend on t explicitly, so it's an autonomous equation, which is the word we'll find in section 2.5 for those. So these green arrows give us our direction field for the equation, and the black lines I've drawn are just 6 examples of solutions with different values at t equals 0. So as you can see, I've picked the value to be 600, 700, 800, up to 1100, and you get a curve for each of them. Now these set of curves are called integral curves for the ODE because they are potential solutions depending on where you start. And I've plotted them all and displayed it all in one graph. So you have a direction field, which are these green arrows that tell you where things are going to go, and these integral curves that depend on your choice of initial condition, your choice of c from the integration condition from before, and then that they are a way to represent your general solution. So let me go back and I'll write all those terms down for you. So we had a direction field, which is basically a plot of dp dt, or dx dt in that case, as a function of x and t, where you draw tiny tangent lines to where the curves are going to go. That we also have a term that I only mentioned once yet, was just the general solution, which is basically just a solution that we have above. It's one that has an arbitrary constant c in it that is yet to be determined. And then we have integral curves, which are a way of visualizing a general solution by plotting it for multiple choices of c. All right, so we have this sort of setup here, but now how do we actually pick the value of c? Well, that means we need to know a little more information. So what if, for instance, like how I set up the Maple code before, we had our function, which is now off the screen, so I'll write it again. What happens if we also knew the value at t equals 0? So what if we had that p of 0 was 1,000, which is one of the curves that we drew on the Maple sheet. So how do we go from there to figuring out c? Well, all we have to do is just plug in t to be 0 and see what happens. So I know by my expression that p of 0 is going to be 900 plus c times e to the 0. E to the 0 is just 1. So this is 900 plus c, which I know needs to be 1,000. Therefore, I have c equals 100. and I have my solution with that initial condition, P of t is going to be 900 plus 100 e to the t over 2. So this sort of setup here, where you're given both a function with a general solution and a value of the function, is called an initial value problem. And the particular value, p of 0 equals 1,000, is called an initial condition. So that's basically the way these solutions come together. You have a general solution that comes from just solving the ODE directly, and then by applying your initial condition in an initial value problem, you can then find the constant c and get the actual solution to the problem. So I'm going to give you guys a couple practice problems to work on this and figure out what this is. I know you actually can't solve the ODEs yet, so I'll give you the solutions, I'll give you the general solution, and then you just have to figure out the constants from there. So I'll give you those to work on, and those should also go on your worksheets for tomorrow in class. So I'll put that up on the screen now. All right, so there's those two problems you guys to work on. Take a look at those, work out the answers, and put them on that worksheet to turn into class tomorrow. Thanks a lot for watching, and I will see you in the next video.